In Chapter 4, we're going to explore discrete random variables and their probability distributions. First, let's define what a random variable is. Well, that's a value that's a result of an outcome of a random experiment. So that's not too unusual a definition for us to grasp. But a random variable that assumes countable values, now these are all numeric, discrete and random and continuous are both numeric values, but the discrete random variable is a countable value. In other words, it's a whole number, such as 1 or 2 or 3. And where a continuous random variable would be an interval. It could be a value that's contained in an interval. So a continuous random variable could actually be a fraction or a decimal. You want to pick several of these to write down on your notes on page 1 for examples. And one I've given you is number of pizzas sold at a pizzeria during a certain month. Another would be number of houses in a block, number of dogs owned by students in our class, the number of late flights of an airline on any given day, the number of customers that visit a grocery store, the number of heads obtained if we toss a coin 3 times. And when you think about this, each of these would be a whole number, a counting number. And that's what I would write beside discrete random variables, counting numbers. In other words, there are no fractions involved. You would never say that somebody owned 3.5 dogs, would you? Continuous random variables, however, do include the possibility of fractions or decimals. Now, usually continuous random variables, while they're still numeric, are measurements, length, time, amounts, weight, and money is often considered a continuous random variable, especially if there's a large number of individual unique values. But most of the time in this class, we will treat money as a numeric or a continuous random variable. Now, if we're dealing with a probability distribution of a discrete random variable, it's going to give us a list of all the possible values of that variable and their probabilities. For example, and this is an example I've put on the middle of page 2, this is a frequency distribution of the number of cell phones owned by families in a given selection, and X is the number of phones owned by those families. And we want to create a probability distribution and make a histogram of this probability distribution. So we have the frequencies. We've already captured the information, captured the data, and we've grouped them. Of the 1,000 families surveyed, 15 of them did not own a phone at all. And you can see that the highest number was owned 2 phones, and that was 455. Let's take a look at guided notes, page 2, and let's work on this relative frequency chart down here in the middle of the page, because that's what we're going to use to calculate and to do our frequency distribution. Now, the first thing you need to do is to calculate the relative frequency of each of the different categories. Now, the categories are over here. Number of cell phones in a household is our categories, and of course the frequencies are here. And our total in the survey, the total number, is going to be 1,000. So you're going to take, for relative frequency, you're going to take the first one. You're going to say 15 divided by 1,000, and you're going to give me a relative frequency for that. Now you're going to do a relative frequency for all of these and sum them at the bottom. I've completed the frequency chart, the relative frequency chart, just like we did in the last chapters. And as you can see, when I sum them at the bottom, it comes up to the number 1, or extremely close to the number 1. So I feel like I've got my frequencies, my relative frequencies correct. Now the next thing you've been asked to do is to create a histogram. So what I would do is come over here to this yellow block, and I'm going to draw a block that represents each of these relative frequencies and where they fall on this chart. So for 0, for example, how many cell phones how many families own no cell phones? Well, 0.015, well, that's going to be way below 0.10, and I'm going to just have to represent that with a small little bar here somehow. And then how many owned 1? Well, that's 0.16, somewhere in between 1 and 0.1 and 0.2, and you can estimate, use your best guess here. Go ahead and finish your frequency chart. So mine looks a little like this, and hopefully yours is close, and that would give me a really good idea of the probability distribution of this data. And as we can see, and we knew this already, but this gives a graphical representation that most families own 2 cell phones, and it was quite a bit of difference in that and the families that own 0 cell phones. We could get other questions answered from this data, but a histogram is a good way to represent our data. Now I want to mention one more thing as we're talking about this relative frequency and the probability distribution. The probability is really equal to the relative frequency in our relative frequency chart. So when we dealt with relative frequency in the last chapter, now we might start calling it probability. There are 2 important characteristics of a probability distribution that you are responsible for, and one of them is that the probability for each probability, it's always between 0 and 1, and that's inclusive. It could be 0 and it could be 1. And the second one is the sum of all the probabilities is always equal to 1. You're going to remember this from probabilities, characteristics of other probabilities distributions that we were dealing with in the previous chapters. So these 2 rules shouldn't be anything new for you. Now let's take a look at another probability distribution of a discrete random variable and see what questions we might ask as researchers that this could answer. This was done by a child psychologist interested in the number of times a newborn baby woke its mother after midnight. There was a random sample of 50 mothers, and this information was taken. X is the number of times per week the newborn's crying waked its mother after midnight. So you can see the probability table has been completed with the relative frequency, which is the probability. You can also see that these are discrete random variables. In other words, the number of times here is in counting numbers, 0, 1, 2, 3, 4, and 5. Now, the questions asked are at the bottom. What's the probability that the number of wake-ups during a given week is exactly 2? Well, for this one, all we have to do is look at 2 times and go over, and we find the probability of 0.46. So that's simple. The next question, what's the probability that it would be 0 to 2? Well, that's going to include 3 different categories, isn't it? The 0, the 1, and the 2. So we would take 0.04, add that to 0.22, and add this one to 0.46 to get the probability that it was 0 to 2. Go ahead and answer questions C and D, B, C, and D, and then come back and check your answers. Now, let's go back and look at these answers. Again, exactly 2 would be a probability of 0.46. 0 to 2 would be 0.04 plus 0.22 plus 0.46, and I came out with 0.72 when I added those 3 numbers together. More than 4 is an interesting question. More than 4, well, this is the only category that's more than 4 is 5, so it would be 0.02. And D, at most 5, means 5 is the most, but anything below 5 would be included. Well, that's everything. So it would be a total the total of all of them is what it would be, which is the number 1. Now, let's look together at creating a probability distribution for a discrete random variable. Now, this is a survey that was taken, and according to our survey, 65% of all students at IRSC have math anxiety. So it selects 2 students at random from IRSC, and X is the number of students that suffer from math anxiety in our distribution here. So we're going to do a probability distribution of X. Now this is done just like a tree diagram, except this time the actual probabilities are inserted. Now, how do we know the probability? Because of the survey that we took that said 65% of that whole population of students suffer from math anxiety. So here's our first student, and the first student probability of yes and probability of no is listed. Well, the probability of yes is 65%, or 0.65. So the only other choice, the probability of no, would be the rest of it, right? And so that would be 0.35. Student 2 could go yes, no, or yes, no based on the first answer for student 1. And so we have written in those probabilities just like we did with our tree diagram, but this time we have added the actual probability percentage here, or decimal, okay? Next, we're going to write down the probability of yes, yes, this first leg here. Well, the probability of yes for the first student and yes for the second student, think about it, that's a joint probability, isn't it? So from what we learned in the last chapter, joint probabilities, we multiply. So we would multiply the 0.65 times the 0.65, and we would come up with 0.4225. We'll do the same thing for the rest of these probabilities. 0.65 times 0.35 for a yes-no is 0.2275. And then for a no-yes, it's exactly the same thing. Those numbers are just reversed order, 0.2275. And then for no-no, it's going to be 0.35 times 0.35, or 0.1125. Let's finish this up by putting it in a probability distribution table. So we list our values for X, which are the number of students with math anxiety, and what are the possibilities? Well, it could have been no students, or 0, had math anxiety, 1 student, or 2. Why does it stop at 2? Because this experiment only selected 2 students, so the most that could have math anxiety was 2. And then we go and we find the probability for each of those. Now, the probability for 0, we've already calculated it. Here it is. That would be the 2 no's. Probability that nobody had math anxiety, 0.1225. The probability of 2 is easy to do too. Look at it. The probability of 2 is up here at the top, 0.4225. But the probability of 1 is really more than just, it takes into account more than one outcome, doesn't it? The outcomes could be yes, no, or no, yes. Now, did you hear what I said? I said it's either this one or this one. So that means I have to take those two and add them together, because that's how I get a union probability, one or the other. So I add 0.2275 and 0.2275 together, and I get the probability of 1 student having math anxiety as being 0.445. Now, what happens next? Well, I take my probabilities and add them together to make sure they equal the number 1, and I've finished my probability distribution. So let's go further. We need to know how to calculate the mean. We also call the mean, of course, the expected value. And we need to calculate the standard deviation of discrete random variables. Now, the mean is calculated as the sum of x times the probability of x. And the standard deviation has a rather complicated formula that takes the square root of the sum of x squared times the probability of x minus the mean squared. So to get the standard deviation, you're first going to have to calculate the mean, then you're going to have to plug it into this formula, and then you'll take the square root. And note that we are not calculating the variance anymore. That's because the variance is only used to get to the standard deviation, and the standard deviation of this is calculated by taking the square root. Now, in this next example, we're going to take the mean of our data on the newborn baby crying and calculate the mean for this discrete random variable distribution, and we're going to calculate the standard deviation. I've given you a table on the middle of page 4, and we're going to use those extra 2 columns to complete this table. This one I want us to do together because it can be confusing the first time. But what I'm going to do is look up here at my formulas and see, what do I need to take summations of? Well, one thing I need to do is sum x times the probability of x. Well, I have x, have the probability of x, but I need x times the probability of x. So I'm going to create a column for that, and then I'm going to multiply x times the probability of x and sum it at the bottom. That will be the sum of x times the probability of x. And then the next thing I'm going to need is I need x squared times probability of x. Well, that's going to be my next column. And down here at the bottom, I'll have the sum of x squared times the probability of x. You should be able to do that fairly easily. Go ahead, finish this table, and then we'll use it to plug in the formulas, the numbers into the formulas, and calculate the mean and the standard deviation. I've finished my calculations, and so you want to check before we go forward. Make sure you're doing this correctly. I'll go through one of these with you just to make sure you know what we're doing. When I said x times the probability of x, of course I'm multiplying this column, the first column times the second column. The first one comes out to be 0 because 0 times anything. The second one comes out to be 0.22 because it's multiplied times 1. The third one is 2 times 0.46, 0.92, and you get the picture. The fourth column, first I have to square x and then multiply it times the probability. So in the first one, I'm still multiplying by 0. The second one, squaring 1 doesn't change anything, so I'm still coming out with 0.22. But in the second one, I'm really saying 4 times 0.46. I'm squaring the 2 and then multiplying. And that's how I came up with these numbers and then summed at the bottom. Now let's look at the mean. What is the mean? Well, the mean basically is the sum of x times the probability of x. Well, I've already got that, or 2.1. So the mean is already done for me when I finished my table. The standard deviation is going to equal, this time, now I've got to take my formula, and I'm going to say the sum of x squared times the probability of x. That's this fourth column. So I've got 5.46, and I'm going to subtract the mean squared. So I'm going to square 2.1. Remember, all of that is still under the radical sign, so if your calculator requires you to put parentheses in there, then please do so. Otherwise, it should work for you as order of operations because it should square the 2.1 first, then do the subtraction, and then take the square root, and that should be fine. I get 1.0247. There's another exercise for you to complete on page 5. It talks about pizzas, and it says Sylvester's Pizza, which prides itself on delivery within 30 minutes, checks. The owner checks to see if he's successful in his endeavor, and then he gathers some data and he analyzes it every week, and he creates a probability distribution. And in this distribution, x is the number of late pizzas ordered in the week, and the probability for each of these values of x is calculated. Now, this chart here is written as we would probably write it if we gathered the information. It's written horizontally. But if I were to put it in a chart so that I could do my calculations, I'd probably move it to a vertical chart like I've done at the top of page 5. So notice how you're going to have to do this in most of your problems, and you might want to just get used to changing the horizontal to the vertical data. So I've taken on that page for you and created your vertical chart, and see if you can complete it with the data that needs to go in it, and calculate the mean and the standard deviation of x. Now I'm going to help you get started with this one because I've given you a different number of columns this time. What I've really given you preparation for doing here is creating one column that says x times the probability of x, and then I gave you a place to put x squared, and then x squared times the probability of x, and maybe that'll help you in completing the summations. But once again, you go back to your formulas and you see which of these columns do I need to sum. Well, I really need to just sum this one. That would be the sum of x times the probability of x, which is going to give me the mean. And then I need to sum this last one because I need it in my calculation for standard deviation. So I've done these calculations that you can check your work, and you can go ahead and fill in and make sure that you've got these right, but you should come up with the mean of your data is equal to 2.5, and then you're going to come up with the other number that you really need, which is the sum of x squared times the probability of x, and that one I came up with 7.7. Now let's fill those into our formulas and make sure that you know how to do the calculations. So I come up with the mean, of course, equal to 2.5, and what that is it's how many pizzas he had late per week. So his mean is 2.5. That's the average, the expected number of pizzas late per week. Then let's do the standard deviation. By plugging in the sum of x squared times the probability of x, we have the square root of 7.7 minus 2.5 squared, which is the mean squared. And we end up taking the square root of 145, which came out to be 1.204 late pizzas per week. Now that would be the number that it deviates from the mean, the standard number that it deviates from the mean. Well, let's take another example and I'm going to let you finish this probability distribution for this discrete random variable. And it's considering a 3-car garage, and it wants to know what's the probability that there will be, cars, the number of cars parked in a 3-car garage. So evidently they've checked and they've seen that the probability of there not being any cars parked there is 0.1, of 1 car being parked in the garage is 0.2, of 2 cars being parked in the garage is 0.4, and of 3 cars would be 0.3. Now if you sum those up, they should equal the number 1. And then you can go ahead and finish this table and create and calculate your mean and standard deviation for this probability distribution. Be sure you do this work on your own before you go forward in the tape. So to check your work, I came up with these probabilities. I came up with this probability, the mean of the probability distribution came up to be 1.9. And then I came up with the sum of x squared times the probability of x, 4.5. Let's take a look at what the calculations look like for the standard deviation. If I plug in 4.5 and 1.9, I would come up with a standard deviation of 0.94. Now, what these mean, and you always have to interpret mean and standard deviation in the units of the problem. And the problem was cars parked in a 3-car garage. So the mean would be 1.9 cars, and the standard deviation would be 0.94 cars. So I'm going to let you take this next example, this next exercise, one step further. What I want you to do is take the narrative and see if you can't fill in the value for x and the value for the probability of x from the narrative here. It says Ellen has music practice 3 days a week. She practices for all of the 3 days, 85% of the time, 2 days 8%, 1 day 4%, and no days 0%. So they're going to select a week at random and create a probability distribution for the data. X is the number of days per week Ellen practices, so you're going to write what are the possibilities down there. She's going to either have no days, or 1 day, or 2 days, and you can finish filling that in. And then you're going to fill in the probabilities that are given to you in the narrative. Next, I want you to calculate the mean and the standard deviation of x. Be sure you do the work before you go forward and check your answers. So what I found from looking at the narrative was that Ellen practiced either 0, 1, 2, or 3 days a week. And it said she practices music 3 days a week. So she either practices all of them, and that's all of the 3 days, 85% of the time. So at 3 days, we put down 0.85. 2 days, 8% of the time. So on the 2, we're going to put 8%, which is 0.08. And 1 day, 4%, 0.04. And no days, or 0, 3%, 0.03. That's our probability distribution. So we're ready now to calculate the mean and the standard deviation. The mean, of course, is x times the sum of x times the probability of x, which comes up to be 2.75. And then we use our sum of x squared times the probability of x to calculate the standard deviation. Here's your calculation for standard deviation. Plugging in 8.01 and subtracting the mean squared gives us 0.67 days. Now we're going to change concepts just a little and talk about something called the binomial experiment. And by doing this, we'll be talking specifically about the binomial probability distribution, and we'll have to use the binomial formula a good bit. We also have, and this is in the beginning of your module, a table of binomial probabilities, which you will get to use on test 2. So you'll have those pages you'll want to be able to tear out and use on test 2. And then we have the probability of success and the shape that we need to be concerned with of a binomial, and we'll of course need to calculate the mean and the standard deviation of the binomial distribution. So first, what exactly is a binomial experiment? Well, there are certain conditions to the experiment before it can be called a binomial. One, you must have a fixed number of trials. Now that means that n has to be just a fixed number. And that's not usually hard. We have to have a number of trials, and we call that n. 2, each trial is an independent event. It means each time you repeat the trial, it's a fresh trial, and it doesn't have an effect on any of the other trials. 3, there can only be 2 outcomes. Now, in other words, If you can phrase a question in your experiment yes or no, then it can be a binomial. In other words, if it could be heads or tails, that could be a binomial. Can someone find a parking space in the city? That would be yes or no. That could be a binomial. Do eggs get hard boiled in 10 minutes? Yes or no? That could be a binomial question. So it has to have just one of two outcomes. If an experiment meets the criteria for a binomial, then what we have is a formula to calculate the probability. Now, what we're dealing with is usually we have to identify certain pieces of the binomial. We identify n, which is the total number of trials, and we have p, which is our probability of success at a trial. Now, a success in a binomial is not necessarily a good thing in real life, but it is whatever the researcher has identified that the researcher is looking for. And so we know the probability of that success. If we know the probability of the success, we also know Q, which is really the probability of failure, which is always 1 minus P, because a binomial only has two possible outcomes. X is the number of successes in our trials, and then of course the number of failures would be n minus X. So what you're always going to identify when you start a binomial is this: n, p, q, and x. You're always going to want to write those things down and identify them. And you're also going to want to jot down what is this researcher calling a success, because it could be the opposite of what you think it is. Once you've identified the pieces, you see the probability of x, which is the probability of whatever number of successes you're interested in, is equal to a combination of out of n things, which is the total number of trials, taking the number of successes and at a time, and that's a combination formula. And then we say times the probability of success raised to the exponent of the number of successes times the probability of a failure raised to the power of the number of failures. So here's an example we can go through together. 83% of millennials surveyed reported having a Facebook account. So 3 millennials were randomly selected from this group. What's the probability that exactly 2 of these 3 students use Facebook? Now, what we want to do is write down, and I've given you room down there, what is n, what is x, and what is p? And then I would also write down, if you know p, you've got to know what q is, don't you? Let's take a look at our narrative closely and see what it's really asking us. What we need is n. Out of how many? Well, 3 millennials were randomly selected, so n is equal to 3. We're choosing out of 3, a group of 3. And they want to know what the probability that exactly 2 of these use Facebook. So x, the x we're interested in, is 2. Now, what are we calling success? Well, our success is going to be using Facebook. Do we know the percentage of millennials that use Facebook? We happen to know that. It tells us 83% of millennials surveyed have a Facebook account. So we can say P, the probability of success, is equal to 0.83. So what do we know? Well, we know n is 3, x is 2, probability of success, or p, is 0.83, so we can say 1 minus 0.3 and come up with q, which is 0.17. The probability of 2 successes would therefore be written as the probability of 2, and it would equal a combination. Out of 3 things, we take 2 at a time, times the probability of success, 0.83, raised to the power of x, which is 2, times the probability of a failure, which is 0.17, raised to the n minus x, well, that's 3 minus 2, or the power of 1. And when I finish that out, I come up with 0.351339. I'm not sure how many decimal places you would be asked to round it to, so you could round, though, easily to 4 decimal places. So I want you to take page 8, and I want you to practice finding the parts of the binomial formula. You're going to want to find n, x, p, and q, and write those down. And then we're going to practice putting this into our formula, putting the pieces into the formula, and coming up with your answers. I'm going to walk through these with you since it can be a little bit confusing, but I also want to note that I've put some instructions for using the binomial function in the calculator, and we'll go through those in just a minute. First, we're assuming that 80% of all Delta flights arrive on time. We're going to test 15 flights, find the probability that 10 arrive on time. What are we calling a success here? Well, we're going to say on time is the success because that's what it's given us as our probability, but also because it's told us find the probability that these arrive on time. Now, on time here matches what we're given, and that always makes it good and easy, so we know we're dealing with the same probability. Okay, so how many flights are we testing? That's our n. There's 15. And we want the probability of 10 of those being on time, so that's the x that we're interested in. We know that the probability of success is 0.8, so the probability of failure is 0.2. And now we can put it into our formula and calculate. We would say that the probability of 10 flights arriving on time is equal to a combination. Out of 15 flights, we want 10 to be on time. And then we would multiply that times p raised to the power of x, and then times q raised to the power of n minus x, which is 5. That's all I really want to do at this point, okay? You can do the math behind that. Make sure you know how to calculate your combination. And you will want to use your calculator to do this, and then you should be able to plug those numbers into your calculator and be able to get your answer. We'll go through the answers in a minute. I'm going to use the calculator to do that. Next, what's the probability of getting 8 questions correct on a 10-question multiple choice test with answer choices A through D? Well, that doesn't tell us really too much, but what do I want to know is questions correct, okay? That's what probability I'm interested in, so I'm going to put down here correct questions or correct answers or whatever, okay? That's my success. How many are my testing? Well, I've got a 10-question test. I want to know about 8 correct ones. That's my n and x. So what is the probability of getting any question in multiple choice correct? And this is the tricky part for this one. If you were guessing, this is really assuming that you know nothing and you're guessing on every question, okay? So we have 4 answers. The probability of getting one right would be 1 out of 4, or 0.25. So what's the probability of getting it wrong, of a failure, is 0.75. Now, of course, this all changes if you study, so note that. All right, so what's the probability of 8 correct? That would equal a combination of, out of 10 things, we want 8 to be correct. And we would say our probability of correct is only 0.25, but I'm going to raise that to the power of, 8. I want 8 correct, right? X. And then my probability of failure is 0.75, and that would be n minus x, so that's going to be 10 minus 8, or 2. And I have set up my formula. Now, if 86% of college graduates start a new job after graduating, I'm going to say they start a new job, what's the probability of 12 out of 130 graduates not getting a job? Well, they didn't ask us, they didn't tell us the probability that they were asking, did they? They gave us the probability of getting a job, and then they asked about not getting a job. This is what you have to watch for, because what they gave us, this is my success, is not no job, okay? Now, in nobody's book is that a success, but in this experiment, it's what they're calling a success, all right? So the probability of success, P, has to be the probability of not getting a job. Now, that's going to be confusing, but let's watch it as we go through. What we're looking for is 12 out of the 130. Well, my number I'm choosing from is 130. Number of successes is 12. Not getting a job is the success. What's the probability of the success? Well, they didn't tell me. They told me Q, the probability of getting a job. So I have to reverse my process. I usually write P and subtract it from 1 to get Q. This time I'm going to write Q, subtract it from 1 to get P, and now I can set it up as normal. But you do have to watch for this. So probability of 12 is going to equal a combination out of 130 things. Take 12 at a time. Notice these numbers, they're huge. This is the reason your calculator learning how to find that combination function on your calculator is extremely important. Even simple calculators have the combination function, so be sure you know how to use it. And then I'm going to multiply that times p, which is 0.14, raised to the probability of the number of successes that I'm interested in. Well, I'm interested in 12 successes. And then I'm going to multiply that times q, which is 0.86, raised to the, n minus x, which is going to be 130 minus 12, which gives me 118. Big exponents. Don't want to do these without a calculator. That's the setup for these problems. Now, I know you can plug these numbers into your calculator and make this formula work. You just have to find the combination and then know how to use it with these different exponents. But I want to show you how to do this with your graphing calculator. First, I've written the instructions for the TI-84 up here. What we need is this blue distribution menu, and I think you can see it. Maybe if I get it a little closer, it's above the variables keys, and I say it's right here. It's distribution. I have to press the second button and then variables to get to the distribution menu. And then I'm going to look down for binomial probability distribution function. That's what that is. So I'm going to go all the way down, and it's not on the first screen. I got to go down until I find it. Now, notice there's a binomial cumulative distribution function. That's not it. You want the binomial probability distribution function, PDF. Here it is. And I'm going to press enter there. Now, this one, mine comes up with a little menu, and it asks me certain values. It asks me the number of trials that I have. Well, I have, and that's really the value for n, isn't it? I have 15 trials here. And then it says, what's the value for p? Well, I'm doing this first problem right here. Okay, so the value for p is going to be 0.8. And then it asks me, let's see, I'll go down to the x value. How many successes am I interested in? 10. That's really all it knows. All it needs to know. It can calculate Q for you, and it knows how to do the combinations. So that's all I really have to have. And I will go down here and paste it. Now, if you don't have that cute little menu, then what you're going to have is binomial probability distribution function, and it'll come up with parentheses. And this is what you will enter. You will enter n, comma p, comma x. No spaces. And don't forget that middle one, the value for p, is going to have a decimal. So I'm going to n, which is 15, comma, 0.8, comma, 10, which is the value for x. And that's how you'll enter it if you do not have the menu to create it for you, okay? But after that, all you do is press enter, and there's your probability. It takes a lot of calculations away from you. I came up with, and I'll just go to 4 decimal places. I'll say 0.103. I'm rounding to 4, so it went 318. I'll say 1032, 0.1032. Let's do the next two real quick. So I'm going to clear this, and then I'm going to go and do binomial again. Let's see it, distribution, and I've got to go all the way back to my binomial PDF, and I'm going to change my numbers. For the second problem, I need n to be, this time n has to be 10, and p, probability of success, is 0.25, and x, the probability, the number I'm interested in getting correct is 8. So I'll go down and paste this, and once again, binomial PDF, parentheses, n, comma, p, comma, x would be the way you would enter it. Be sure you close parentheses, and then you would hit enter. And this time it's an interesting sort of a number. It has e to the negative 4, which means take the decimal and move it in the negative direction 4 places. Well, that's going to mean that I'm going to have 0.00038, which would round to 4, right, if I go to 4 decimal places. So I've got 3.86, and then I have an e to the negative 4. So when I take that decimal and I move it 4 places in a negative direction, I get a very, very small probability. In other words, that one tells you study for your test. Okay, next, let's take a look at C. I'm going to clear it again. I'm going to go back to second distribution, and I'm going to go down to binomial probability distribution function. And this is where, when it has the numbers that are so large, this is where it really helps me. Out of 130 trials, I have a probability of success of 0.14, and I'm interested in how many successes. What was the X on this one? 12, right? I'll go down and paste it. And once again, N, comma P, comma X is the way it's formatted. No spaces or it'll give you an error. And I get my answer. This probability is 0.030, and it would be 48, so I'm going to round it to 5. Let's take the second exercise, and I want to see how far you can get without my help. So let's see if I can talk you into getting started. FedEx estimates that 0.1% of the packages mailed through this company are damaged during delivery. Okay, they've given me the percentage that are damaged. Suppose the corporation mails 10 packages on a certain day. Find the probability that exactly 1 will arrive damaged. So the question is, of a success is damaged, right? A damaged package. And they have given me, these are damaged, they have given me the probability of it being damaged. But now look at it, it's 0.1%. So that means I have to move the decimal place. If I'm going to get rid of the percent sign, I've got to move that decimal 2 places to the left. The probability of it being damaged is 0.001. Now I want you to note that because that's an easy mistake to make. Be careful with that. Now go ahead and fill that in and make sure you've got your probability, and I'll work that problem completely. Use your calculator to calculate. And then find the probability that at most 1 will arrive damaged. Now at most 1 means that it could be the probability of 0 or 1. So there's going to be 2 of these that you have to calculate. Fortunately, you will have already calculated one of them, so you can just calculate the second one and add the numbers together, because it's going to be either 0 or 1, and that would help us to, that would be an OR probability. Now here's the worked solution as I see it. We're out of 10 packages is what we are dealing with. That's our number that we start with, and we want the probability that 1 is going to arrive damaged. That probability of any package arriving damaged is 1.1% or 0.001. And so the probability that it would not arrive damaged would be what? Well, we'd have to say 1 minus 0.001 or 0.999, as that's the probability that it would arrive undamaged, which we would call a failure here. So here's our probability of 1. It's going to equal a combination out of 10 things. We take 1 at a time, and then we're going to say probability of success raised to the power of the number of successes times the probability of a failure raised to the n minus x, or the number of failures, and we would use that calculator to calculate that. Calculator or do the math, either one. But I'm going to use the calculator. I'm going to go to my binomial function, and I'm going to enter 10 trials, and I'm going to enter 0.001 as the probability of success, and I'm going to enter 1 as the number of successes I'm interested in, and paste. And this is what it looks like pasted in. And my answer comes out to be 0.0099. I'll round it to 4 decimal places. So next, I'm asked to find the probability that at most 1. Well, that means I have to do probability. I've already done the probability of 1, so now I have to do the probability of 0, right? So I'm going to say 0 or 1. Let's go ahead and say I've got 10 trials. I've got the same probabilities. And I just need to calculate the probability of 0 because I already calculated the probability of 1. So I'd say that's a combination out of 10 items. Take 0 at a time. Multiply the probability of success to the number of successes. That's 0. And the probability of the failure of Q times the number of failures, well, this time it would be 10. And let's see what our calculator says about this one. So let's go to the distribution menu and down till we find the binomial probability distribution function. We've still got 10 trials. We've still got the same probability of success, and this time we want 0 for the number of successes. What do we come up with? Well, 0.9900 is what we came out with. So now all I have to do is say the probability of 0 or 1 is equal to the two of those added together, 0.0099 plus 0.9900, well, that's easy math. I don't even need a calculator for. 0.9999 would be my answer. Now let's just continue. I'm going to continue working in your guided notes for a while because this is fairly complicated, and I want to this time construct that binomial probability distribution. I want to go through the steps so you'll begin to see how it's created and how it looks, okay? And maybe it'll help you to understand it. First of all, I have an example that says, according to the survey, 8% of Americans are millionaires. X is the number of American millionaires in a random sample of 3. Now we want the probability distribution of X. So first you have to ask yourself, what's in? Well, we took a sample of 3, so that's in. And the probability, or P, the probability of being a millionaire, well, this says 8% are millionaires, so that's going to be 8% or 0.08. So the probability of not being a millionaire is 1 minus 0.08 or 0.92. Now let's write down, let's go ahead and fill in our formula and write these down, okay? And just see how it works, okay? So what I'm going to do, probability distribution, I want to create the entire thing. I want all the possible values for X. Now if I have a sample of 3, I could have either a 0, a 1, a 2, or a 3. Now note, every time you have a sample, you're going to have one more possibility than that because you're going to have to add the 0 in there, okay? So you're always going to start with the 0 and it's 1, 2, or 3 if you're creating the entire probability distribution. So what's the probability for each of those? Well, I can calculate them. The probability of 0 would be out of combination of 3 things. I would take 0 at a time, and then I'm going to say P, which is 0.08 raised to the power of X, times Q, which is 0.92, raised to the power of n minus x, which is 3, and I would do that calculation in my calculator. And then I would say probability of 1. Well, this is going to be out of 3 things, take 1 at a time. Let's just fill this chart in. Out of 3 things, I'm going to take 2 at a time. Out of 3 things, I'm going to take 3 at a time. Okay. And then something else that I always know. I know these are always going to be the same P and the same Q, don't I? I'll go ahead and put the P and Q in, remembering that I haven't put the exponents with them yet. Now let's put the exponents in. I need this to be to the P raised to the power of X. Well, X in this one's 1, 2, and 3. And Q's are going to be sort of the opposites of that, the rest of it, right? Because this exponent plus this exponent has to always add up to whatever n is. So 1 plus 2, and 2 plus 1, and 3 plus 0. And I would have my exponents correct. And you would go ahead now and type these into your calculator, and I would let you do that and come up with these probabilities. Now I came up with 0.77868. I'll round it in a minute. This one I came up with 0.2031, and I rounded to 4 actually. And then the next one, or 5, the next one I came up with 0.01766, and the next one I came up with 0.00051. Let's put them in our chart with 4 decimal places. This gives you practice rounding to the 4th decimal place. 0 would be 0.7787. 1 would be 0.2031. 2 would be 0.0177. And 3 would be 0.0005. There's my probabilities of x. So when I add these together, it should come very close to the number 1. Because of rounding issues, it might be a little bit off, but it should still sum the number 1. And that is creating your own binomial probability distribution, and all you had to be given was this really short narrative at the top. Just a couple of sentences, and you should be able to create the distribution yourself. Now, let's take a look at a table that's been created for you called the Binomials Probabilities Table. And it works for certain values. There's certain restrictions to it. The table that you've been given, and you can find a more extensive one online if you were to look for one, but the table you've been given and the one you'll be allowed to use on the test lists the probabilities of x from an n of 1 to an n of 20. So if you go down in that table and you're looking at the values for n, which will be on this far left side, you'll see it goes all the way from 1 to 20 on the last sheet. It also lists all of the x probabilities for each of those values. So for an n of 1, you have an x of 0 or 1. An n of 2, you have an x of 0, 1, 2. Remember, I told you, you always add that 0 in. So for each n value, you'll have one more x value. And it goes on until it goes all the way to 20. Now, the table gives us certain probabilities. Not all probabilities are listed in the table. It lists the probability of success. It gives us the p-value of 0.1, 0.2, 0.3, 0.4, and all the way over here to 0.9, but you're going to note that 0.47 is not here, neither is 0.26, but only these probabilities are listed. However, this is the important thing about your table. If you have one of these p-values and you have a sample size of 20 or less, then all the calculations have been done for you. All you have to do is look it up. You will have this on the test so you can use it. So let's practice. Let's look at this sheet I have up here, and you should pull out your binomial probability table. It's at the first of module 2, so that you can be working with me on it. But I'm going to say I want the probability that x is equal to 3 for an n of 6 and a p-value of 0.3, okay? So an n of 6 is right down here, n of 6, and then I need the p-value, or the x value, to be 3. So it's this row is the one it is right here. And where is p 0.3? Well, it's this third column over. So the value I would be looking at would be 0.1852, and it's as simple as that. Now, like I said, and I wanted to fill these in to make sure you understood, the n values are from 1 to 20 in the table you've been given, and these only selected values of p, probabilities of success, are listed on this table. But let's use the table and see what we can find with these 4 questions, and you'll see how valuable the table is as we go through and do this together. There's a survey that says 60% of college students work full-time while they're attending school, and the remaining 40% said they don't work or they work part-time. So we suppose this result is true of the current population, and we're going to look at a sample of 6 college students. Now we're going to use the binomial table to answer these questions. Find the probability that exactly 3 of these 6 students will say they work full-time. Now, you still need to identify the pieces to the binomial. A success for this one is working full-time, and that's what they're asking about, working full-time. And that's my success, so I need to make sure I identify that. And then I want n, and I'm going to say n is going to equal, well, out of a random sample of 6, right? So for all of these questions, n is going to, that's the probability of exactly 3. So that's the x value I've been asked about. Now I also need to know p. And p is these work full-time. So this is the probability of working full-time. It does match what I've been asked in my question. So I can say p is 0.6. I realize when I'm looking at this that I have an n that's 20 or less. I have a p that is on my table. All I have to do is go and look it up, and I will have that probability. So I will know the probability of 3, and I'll write that down. Go ahead and look it up in your table. So let's take a look at your binomial table. This is the one that, like I said, is at the beginning of Module 2, and sometimes it's really handy to have a sticky note available when you're dealing with this table. I'm going to go down to where n over here on the side is equal to 6 because that's my n, and then I want to go to find x equal 3, so that's this column right here, this row right here. Now the only other thing I need is a p of 6. Well, a p of 6 takes me over to right this column here. I think I've got it. So when I'm looking for, and I check it, n of 6, x of 3, and then probability of success is 0.6, I find my answer is 0.2765. Let's fill that one in. Probability of 3 is 0.2765. Let's look at the next question. The probability that at most 2, now remember, at most 2 is tricky. It means it could be 1 or 2, but it could also be 0. So the probability of at most 2 is going to include, it's going to be probability of 0 or 1 or 2 or 2. So that's going to be 3 of them that I'm going to want to add together. Now look, I've got the same n, I've got the same x, I've got the same p, and they're still saying work full time, so I'm dealing with the same success there. So I want 3 numbers I can add together. I'm going to go back to where I was, n of 6, x of 3, probability of success 0.6. I'm on that same row. And this time I want either 0, right? Not on the same row, but I am in the same column. I want either 0 or 1 or 2. So if I'm dealing with this column, let's see if I can put it here for you. I'm dealing with this column, that's the 0.6 column. There, you can see it. And I want 6 in my n, and I want an x of 0, 1, or 2. Really, I got these 3 numbers that I need to write down. Now, that's simple, and then I just add them together, don't I? And I come up with my answer. So probability of 0, 0.0041. Probability of 1, 0.0369. Probability of 2, 0.1382. And I could add those easily on my calculator, 0.1792. That's the probability at most 2. Let's do another one. Probability of at least 3. Okay, so it's going to be 3 to 6, right? If it ends at 6, probability of 3, or 4, or 5, or 6. Now, if you're not using the table, you're going to have to do 4 calculations and then add them together. That's why the table's so nice. So let's look them up. We're still dealing with a p of 0.6. We're still dealing with the same n value. Our x's are going to be 3, 4, 5, or 6 this time. Let me see if I can find those. So this time, what I've got is still in that same column, which I can't seem to show you. Hey, there I got it. So still in the same column, 0.6. I'm right here. And this time, I'm over here. I want 3, 4, 5, or 6. Well, it would be 3 right here, all the way down to here. So I've got these 4 numbers that I will want to add together, okay? I'm going to write them down. That's going to equal 0.2765 plus 0.3110 plus 0.1866 plus 0.0467, and when I add those 4 numbers together, I get 0.8208. All right, next question. Find the probability that 1 to 3 of these 6 college students. So that's the same number, same x, same n, same p, but the x's change. I need a probability of 1 or 2 or 3. But I'm looking at the same place. I'm looking at the same n, so I'm still dealing with 6 here. I'm looking at the same probability of success, so I'm still dealing with this same column. I'm going to turn my sticky note so I can get it down there again. I can make some more notes on it. All right, so here's my column. What do I want? I want 1 to 3. This one is 1. Whoops. 2, and 3. Those are the three numbers that I would be dealing with. 0.0369 plus 0.1382 plus 0.2765, and that's going to equal 0.4516. So you can see how simple it is to do this with your binomial probability table. Now, when can you use it? Well, you can use it anytime you have an n value that's 20 or less, and you have a probability that's one of these that's listed across the top. Now, your table is a little bit different from the one that I showed on my slide, but just remember, this is going to give you a few more probabilities, okay? So let's talk a little about the shape of the binomial distribution. Now, this is important, an important concept for you to know, is that a binomial distribution, a binomial probability distribution, is always symmetric if p is equal to 0.5. It will be skewed to the right if p is less than 0.5, and it will be skewed to the left if p is greater than 0.5. Now, the last thing we have to do when we're talking about binomials is to be able to calculate the mean and the standard deviation. You knew we were going to have to do that, didn't you? So these formulas will be the easiest that I have given you for anything, okay? The mean of a binomial is equal to n times p. That's it. And the standard deviation is the square root of n times p times q. Let's look at an example together. In my example, it says that roughly 10% of people are left-handed. Now, this is according to a University of College London researcher who wrote a book chapter on history and geography of left-handedness. So we're going to assume this is true of the current population of United States adults, and we take a sample of 50 U.S. adults, and they're randomly selected, so it's a good sample, and X is the number in the sample who are left-handed. We want the mean and the standard deviation of this probability distribution. It sounds like they haven't given you enough information, but let's look. What are they calling a success? Well, a success in this case would be being left-handed, right? Because that's what we're looking for. And therefore, failure would be not left-handed. Well, the only other choice, if you're not left-handed, you're right-handed, right? So, how many are we sampling? Well, go back to your survey. They took a sample of 50, that's my n, and they say we're going to assume that this percentage, 10% are left-handed, applies to our population. So we're going to say probability of left-handed, probability of success, 0.1. Therefore, the probability of failure, 0.9. And let's calculate the mean. Well, it's simple. The mean is going to be n times p. And that's going to be really easy for us to do. 50 times 0.1 just gives us 5. And then the standard deviation is going to be the square root of n, 50, times p, 0.1, times q, 0.9. All of that is under the radical sign. And when I use my calculator and do that, I go to 4 decimal places. I get 2.1213. Make sure you try it on your own. I have people all the time who say, my calculator didn't come up with that answer, and it's because they've done something, they're not really sure how their calculator is working. So make sure you're getting the right answers. Now, the next thing I've got is an activity for you to do on your own. It's the same thing, basically. 10-question multiple choice test, 4 options, A through D, and it wants the mean and the standard deviation of a success. Now, a success is a right answer, okay? Probability of a right answer, if you are guessing, is 1 out of 4, all right? So here's your p value. It's going to be 0.25. I'm just going to help you out with that. And then, of course, the next one says, a report states 80% of adult smokers started smoking before turning 18 years old. The mean and the standard deviation for the number of smokers who started before age 18, and that's your success. I know that is not a success, but started smoking before 18 would be my success in this thing. Just like this one, success is going to be a right answer. Okay, so be sure you write the successes down, okay? What is called a success in the experiment, and go ahead and complete that activity on your own. When you do, you'll be finished with Chapter 4, and you'll be ready to do all of the work associated with it in the homework and quizzes.